Okay, hello everyone again. Thank you for joining. My name is Dasha. I am a community manager at Super BI and your humble host for today's session on data quality for computer vision. We all know that every day we rely more and more on data to power many, many systems, not only machine learning, but data is so ingrained in our lives that we almost take we trust it and take it that it's autonomous for granted, but in reality, all right, it's managed by people. So mistakes and biases are definitely making their way into it. And so with ML specifically and computer vision including, of course, logic is no longer coded in to the programs, but the program learn the behavior from the data, which makes quality of this data just as important, right, as code, I would say. In production machine learning systems, data typically comes from many sources, and it's often inaccurate, imprecise, inconsistent, or has other quality problems. So hence, deliberately thinking about and ensuring data quality in production is really crucial at this point. If you're like me, though, data quality in ML remains a somewhat vague term that can cover a number of major or minor issues in various stages of production. But even more confusion, again, and I'm talking about me, let me know if you guys can relate, arises when we deal with unstructured vision data. Luckily, our guests here today know all about it. So I'm just gonna really, quickly introduce them before we start. So Alessia is the CEO and founder of WhyLabs. WhyLabs is an AI observability company building tools to power robust and responsible AI development. Prior to WhyLabs, Alessia was the CTO in residence at the Allen Institute for AI, where she evaluated the commercial potential for the latest AI research. She also spent 9 years at Amazon leading ML initiatives, including forecasting and data science platforms. And I would like to note that Alessia is also founder of Robust and Responsible AI Community. It's a global community of AI practitioners who are committed to making enterprise AI technology responsible. Welcome, Alessia. Thank you for joining. And sorry. Moving on to Hyun. Hyun is the CEO and founder and co-founder of Super BI. Super BI is an ML data ops platform that helps computer vision teams to automate and manage data pipeline from ingestion and labeling to data quality assessment and delivery. Hyun initially studied biomedical engineering and electrical engineering at Duke, but shifted from genetic engineering to robotics and deep learning. He pursued PhD in computer science at Duke with focus on robotics and deep learning, but ended up taking leave, to further immerse himself in the world of AI R&D at corporate research lab. And that's where he started to experience the bottlenecks and obstacles that many companies still face this day, like data labeling and management. Welcome, Hyun. Thank you for joining. I think we're good to start. Well, let's start with Alessia. Can you tell us a bit more about your experience working in production ML prior to founding the WhyLabs, and basically just walk us through a little bit of what inspired you, what pushed you to, start your company.
Excellent. Thanks for having me here, Dasha and Jan. I'm really excited to participate and share some of my experience. So, as you mentioned, I spent many years working at Amazon, and I was very fortunate to experience the very beginnings of AI adoption at a company like Amazon, the company that puts their customers first and the customer experience first, which means that as AI is getting deployed, you really focus on quality of experience and robustness of experience. So I had the fortune of building an internal machine learning platform in the company and watching the adoption of this platform and how every team that gets AI to production in the company was able to benefit from a more streamlined operations, from continuous testing, from continuous monitoring, from reproducibility. It was very inspiring, actually, watching team go from kind of scrambled operations that rely on a lot of tribal knowledge and Jupyter notebooks, frankly, to something that is more systematic. It was magical. So once I experienced that, I got very excited about watching how this wave of tools is going to impact every company, every organization out there that is relying on AI. And I decided to leave Amazon and find a way to participate in building this tool chain, which then, I left in 2017 and 2019. The community coined MLOps, and now MLOps is, a fairly colloquial word in the community. So I left Amazon with the idea of participating in this wave, and essentially building the tools that I've seen and built at Amazon and making them available to every practitioner out there. So that's what inspired WhyLabs.
Thank you very much. Well, same question to you, Hyun, then. What inspired you to start the company?
Yeah. So prior to starting the company, I used to work as a machine learning computer vision engineer at a corporate research lab, as you introduced earlier. And I worked on, various projects from like self-driving or game AI, like StarCraft AI, or like unsupervised learning. And, in all of these, projects, I felt that, the AI development process was very slow. Right. So, I started Storb AI because I believed, machine learning development process was too inefficient. And, I strongly believe that, AI will be the next breakthrough for mankind, like, electricity or like personal computers or internet. But the pace at which AI tech was evolving seemed to be too slow. Right. So, like, it's funny because in academia, like tons and tons of new fancy research papers were like being published every day, but the rate at which companies and industries adopted AI seemed to be too slow. This was especially the case for like large enterprises. I don't know if that was the case for you, Lisa, but that was even more so for like traditional industries and enterprises. So, and the biggest bottleneck that I identified was the training data. So that's how we got started. We're founded to solve the training data inefficiency problem.
Thank you, Hyun. Okay, so actually, let's move on. Let's jump into the next question with you, Hyun.
Yep.
Just logically, starting from the earlier stages of production, right? So what does data quality actually mean? And how do you define it, and what aspects you see of it that is important to pay attention to in the whether it's model development stage, like really the first stage before production, exploration, labeling, and exploring the data set.
Right. So I think I can speak more on the model development stage rather than production. I think, Alicia, you have more experience in that side of the world. So in the model development stage, I can think of data quality in two different groups. So one would be the annotation quality or the labeling quality, And the second bucket would be the raw data quality, right? So for annotation quality, there are a couple of things. One would be the accuracy of the annotations. So things like, are the classifications correct? Are there any like false positive bounding boxes, false negative bounding boxes, or if you have a bounding box or like a polygon annotation, are those tight enough around the object of interest? So that's one aspect of annotation quality. Another aspect to that is also the consistency of the annotations. So let's say you're a self-driving AI startup, you need to label like 1 million images of cars, right? Do you include the side mirrors in the bounding boxes, or like, do you not include it? Like that has to be consistent throughout your entire data set. And also things like occlusion, right? Let's say your car is occluded by a pedestrian that's standing in front of it, right? Do you draw a large box for the entire car, or do you draw like two separate boxes for like left side and right side of the occlusion, right? And those kind of things should be consistent throughout your entire ML lifecycle, right? And things like this can throw off your model's training when it's not nailed down properly. And then another thing that's obvious but often overlooked is the distribution of your classes, right? Obviously, if you have a well-balanced data set, that's going to throw off your models. So that's the annotation quality side of things. And then the second bucket, like I said, is the annotation or the raw data quality. So these are things like simple things like quality of the images, like the blurs or lighting conditions. Those needs to be checked upon. And also the big piece to raw data quality, I think, is the coverage or the diversity of your raw data set, right? So again, going back to the self-driving use case car data set, like you need to check whether you have enough diversity in your background, for example, whether that's weather conditions, lighting, time of the day, camera angles, so on and so forth. And also diversity in the object of interest itself. For example, if it's cars, do you have enough variety in the like car make, car model, color, orientation of the colors? Are the doors or trunks opened, closed? Are the headlights on? Stuff like that. So like if something's not in your data set, basically you shouldn't expect your model to learn it, right? Of course, it learns to generalize. Like that's the whole point of training a model. But there are limits to how far a model can generalize. So if you want to cover all the you want to cover all the corner cases and edge cases in your training data set. So yeah, that's what I think about data quality in the model development stage.
I kind of have a follow-up question. I actually can imagine how to, or I don't know, deal with this kind of data quality issues in the development state for structured data. But what about exactly vision unstructured data? So how can I explore the distribution, right? What can I do to see that or like how can I visualize it, or how can I check for data labels? Are they accurate? Are they consistent? Or maybe how can I preempt them? So do you have some actionable advices? Because vision data sets are huge and really challenging to manage. So
yeah, so for checking the distribution of annotations is easier because you can just use statistics to do that. For example, class frequency, you can just draw like histogram and compare, or not just for classes, but for example, like within the same class, you also want an even distribution of, for example, like aspect ratios, right? Like for example, person class usually are like tall and thin bounding boxes, But let's say your model in production encounters a person like lying down flat, right? That's flat and wide, right? So that might throw your model off. So things like these you want to check, and that's more or less pretty simple using statistics. But for checking raw data quality or diversity of your raw data, that's more difficult to do for computer vision. So you can't just do like pixel level comparisons. So there are things like deep learning features, like embeddings. So you need to calculate those embeddings from your images and then do a bunch of operations on that embeddings. So it could be things like clusterings on those embeddings, or trying to find distribution of embeddings, or you can plot those into like a two-dimensional space after you do dimensionality reduction on your embeddings, and then see whether you're missing anything, and see if what kind of similar objects, visually similar objects or images you have in your data set. So those are some of the techniques. I don't think this kind of technique is very mature in the industry. It's still like exploratory phase. Different companies use different techniques, but it's something I think will be very promising in the near future. And it's also something that we provide as a company. It's on closed beta right now. So it will be public soon.
Yeah, it sounds like a lot of work as well to set up running those systems as well, to just being able to explore and understand your data set, computer vision data set. Yeah. Thank you, Hyun. Moving on to Alessa. Alessa, same question to you, but in your area of expertise, how do you define data quality and its parameters when we already have a model in production?
Yeah, similar to Hyun's answer, there are a few different kind of categories where data quality applies. One of them is feature quality, so similar to kind of drawing parallels to the raw data. By the time you're in production and the model is invoked, the raw data is already turned into features. Making sure that the quality of that feature data is consistent on the kind of pixel level, as Hyun was mentioning. So for example, in the computer vision use cases, if you have sensors that are partially obstructed, or if you're working with aerial images and you have images that have, cloud coverage of 50-70%, it's very hard to use such images, and definitely the model would not be accurately marking whatever objects you're trying to extract. So data quality of the features that are coming into the model. Then there goes kind of this concept of training, serving, skew. So by the time we're in production, we already have a concept of what the model is familiar with, right? And I wouldn't specifically put it in the data quality realm, but it is kind of a concern of a similar category. So making sure that your model is seeing data that is consistent with what it was trained on. So similar, kind of drawing parallels to the previous answer, where if your model is trained on seeing a lot of people that are standing up, and you're trying to count, for example, people, and then you're essentially suddenly seeing images where I don't know, people are always laying down. That is kind of an example of a drift, and it actually could happen that the image is just rotated when it goes in to the model for prediction. So recognizing when such drift happens, I think, is also going to affect the performance of the model and could fall under this similar category of data quality. And then kind of the way you catch these issues as both at the point where the data goes into the model, so at the point of model input, and at the point of the model outputs. So watching, for example, whether the bounding boxes that your model is producing are consistent with the shape and distribution and number and size of bounding boxes that you have seen during training. So a good example is if you for example, trained a model to recognize veins and arteries on an ultrasound. And typically in your training data, you see, about 2 or 3 bounding boxes that your model typically training evaluation, you see 2 or 3 bounding boxes that your model recognizes, or in your annotated data, that's the distribution. And then when your model's in production, it consistently outputs like 20 different arteries in every image. That is a very good indication that something is not going right, either with the data quality or with kind of the shift in the data that the model is seeing. So when it comes to production, I guess to summarize, there are a few different categories of there are a few different places of where you would look for problems with the data or data quality issues. That is upstream to the model at the model input point. It could be even earlier on. So for example, making sure that your data providers are providing data that is coming from the types of devices that you expect, because of for example, camera changes and the resolution on the camera changes, that model might not be ready for these types of inputs. And then on the model output side, watching to make sure that the outputs, the bounding boxes, and the distribution of classes is consistent with what you have seen during training evaluation. That also falls under the category of data quality.
Can I ask a quick question follow-up?
Yes, please.
So I'm just curious. You mentioned the difference in basically how the distribution of classes could be different for your training data versus in production data. Is that always like an indicator of drift? Because let's say your model is in like a, for example, manufacturing scenario where your class will be inherently skewed, right? But then for training, you want your training set to be more or less evenly distributed. So, for those kind of things, you expect the distribution to be different, right? But, just curious if you've seen other cases like that.
That's a very good thing to point out. And I think especially in things like anomaly detection, if you're building an anomaly detection system in the manufacturing pipeline, this becomes a very important thing to recognize. So, you want to show your model as many examples of anomalies as possible, but in reality, you wanted it to see as few examples of anomalies as possible, right? So I think in that case, using kind of this direct training serving skew parallel may not be the best. The alternatives to that, so you could either use your evaluation distributions, if your evaluation distributions are reflective of the real world kind of expected distributions, or you could essentially build a baseline kind of as a moving window. So you look at, how many anomalies have you seen in the past 2 weeks, and that becomes your baseline rolling over. That's kind of a secondary, I would say, measure. And this type of rolling window kind of saying that, okay, my past has been fairly good quality and fairly a reliable indicator of things going well. So I'm always going to look 2 weeks in the past to see whether I'm different today from what I've seen in the past 2 weeks. That's kind of a very good way to augment the training serving skew kind of monitoring and baseline, because it gives you a more well-rounded kind of indicator, especially important in situations like anomaly detection, for instance.
Thank you.
Thank you, guys. You, Alicia, you mentioned you started to talk or data drift, right? Or let's say what kind of drift that we should be aware of. I know there is more than one kind, and it's really confusing for me sometimes. So how do you deal with that? How do you know which one is which, and when, basically you should decide then what to do with it, or whether nothing needs to be done and that's okay?
It's actually a pretty involved, I would say, exercise to understand what kind of drift you have, where it's coming from, and what you should do about it. Conceptually, kind of we think about drift in two places, maybe three places. So your kind of your environment could be different from what the model has observed when you trained it, and it could be different for a number of reasons. For example, one of the reasons it's different is, let's say, before COVID, people who showed up on cameras were typically not wearing masks. And as soon as we went into the pandemic, probably everybody showing up on a lot of cameras that are installed in kind of public places are wearing masks. So any models that were trained to do facial recognition or even just people recognition were likely thrown off. So that's an example of drift in the real world. Another good example of drift in the real world is, let's say a model has been deployed and it's essentially kind of augmenting human decision making. So let's say a doctor is using an AI model that marks X-rays. And if the doctor was convinced that this AI model is really reliable and works really, really well, and they trust it, then they would be, very inclined to save time just to agree with it consistently, and essentially their behavior of how they make decisions about particular X-rays is going to change. So that's another example of drift. Or, for example, a third example of drift is when your model has seen a certain number of classes. So what's a good one? Let's say you trained your autonomous driving model to recognize cars, and then you deployed it somewhere in Italy, and there are a lot of Vespas there, and that's a kind of brand new class of objects that the model has not observed before. So that's an example of concept drift. So now, how do you recognize these things? Well, when it comes to kind of the drift that happens in the real world, what you try to do is look for indicators that the inputs into your model have changed, that the data that your model is seen in production is different from the data that you have seen during training evaluation. And we can dig into this for a really long time. So there are different ways of recognizing it, especially when you're working with images. And as Jan was saying earlier, you can do simple statistical things. You can, count pixel distributions. You can see kind of lighting conditions, brightness, saturation, color channels, kind of simple statistical tests. These would actually get you pretty far. But, when it comes to analyzing image quality, kind of the next step, you can start understanding whether the embeddings have shifted from what you have seen during training, whether there are new clusters introduced, and so on. And then finally, I think especially in computer vision systems, there's always a fallback on a human, because there's only so far that we can go with these quantitative kind of machine tests that we can run. And then if we are still seeing something, let's categorize it as weird in our machine learning pipeline and production, maybe the outputs are not consistent with our expectations, or just simply, our customers are calling us and saying this thing doesn't work. After looking at all the statistical tests and all the embeddings tests, I think falling back on the human and saying, does this data look different? What is different about it? And so on. And then when it comes to analyzing the drift that's happening kind of on the output level, so let's say the Vespa example, there you can track, for instance, how many objects is your model recognizing per minute on the road, and what are the sizes of these objects, and start watching whether there's a drift in that statistic. So if suddenly your model is not recognizing any objects, but you have some additional, let's say, additional indicators that there are objects around you, that is a very kind of good signal of drift. And those additional indicators are like the car is not driving very fast because it's constantly waiting on something, but your model is not recognizing any objects. Or, for example, your bounding boxes just look very strange, similar to people. So like cars have a certain, size of the bounding boxes when they're marked and within the certain proximities. Vespa is going to be very different. So recognizing when this changes dramatically is kind of a reason for, well, first of all, a reason for further evaluation, potentially a reason for human intervention and analysis, and definitely a reason for alerting the operating team.
Thank you, Alicia. That takes me to, in my mind, the next question, which I believe, Alicia, is your question to Hyun. But that's really like, how do we close this loop, right? Once we identify gaps in the initial model training, and the gaps between that and the post-production or post-deployment data. How do we close this loop? And this is, again, just FYI, this is Alyssa's question that you wanted to ask Hyun. Sorry, Alyssa. Because Superb AI helps to manage data and, labeling. So I feel like, Hyun, you have lots of thoughts on this.
Yeah, so there are a couple of ways that we help close a loop. Let's say model in production, or even models in development phase. You find some errors in your model, and then you always have to go back to the data side of things. That's the whole point of data-centric AI, right? So one way, the simplest way we support teams with this is basically have the clients upload post-production model inferences, or during experiments also upload model inferences to our platform, and just have the labelers audit and review the inference results in real time, right? And then just use the audited version 2 data set to just retrain the model and just repeat that over and over. And as time goes by, you'll have less number of errors in your model inference. Thus, you'll need less amount of manual human input to iterate upon that cycle. So that's the simplest way. The second way, which I mentioned earlier that we're beta testing right now, is the data curation feature, right? So it's an automation feature that helps find rare or edge cases in the data set. It does a lot of other things, but one of the features does that. So these rare cases are often the ones that the model in production will fail on. So with this feature, we help users identify the patterns or clusters of data that we expect their models to perform poorly on. So, and then we can even do that before deploying the model into production by analyzing the training data that the models trained upon, right? So with that information, users can then, able to collect more of these rare cases to enhance their data set and thus improve the model accuracy, right? So that's the second way. And then third, something that I want to do in the future as a company is integrating with model deployment or monitoring platforms like WhyLabs. So using tools like WhyLabs, our clients have a better way to monitor their model in production, and then they can seamlessly get alerted and then get back to the drawing board and do data collection, data labeling, data analytics, right? So that's what we want to do in the future. Hope you like that answer, Lisa.
Thank you, Han. So I will move on to one of the last questions, so I can leave some time for questions from audience. It still feels like there's still a lot of teams that work on an HML project, which which makes like a lot of handoffs happening or have to be happening, a lot of communication between different teams involved. And so there are many things that we cannot automate in this process of, assuring data quality and preparing new data sets for training. And so very general question, but I'm curious what you guys think. Regarding general, data preparation ops, data ops, what are some critical aspects that ML teams are currently overlooking that eventually will be hopefully common practice, or really have to become a common practice? Otherwise, we'll fail this whole ML in production thing. Alice, I'll start with you.
I love the fail the whole ML in production thing. I think there should be a separate conference on that. So I think my answer would be very similar to what Jan just alluded to, which is machine learning development is not a linear process. It doesn't have the beginning and the end. It's very cyclical, and there are many cycles throughout the kind of life cycle. And I think these cycles, we're still discovering what are the meaningful cycles and what cycles could be automated. So one example is once you have a model in production and you're monitoring and you're recognizing that your model is not performing well, you are able to close the loop, as so to say, and for instance, communicate all the way to the data preparation step and say, these are the gaps that I'm seeing. These are new categories of images or new categories of data that need to be annotated, prepared. A model should be retrained and pushed through the few stages of evaluation, deployment, and so on, probably pushed into like shadow mode, and then we will analyze whether that made a difference. And as much the more automation there is in these steps, kind of the faster the cycle goes, the less error prone it is, because typically human handoffs is what introduces a lot of errors, and the more reliable I think the software that we build. And these cycles, I think we have some sense. So the one I just described is the simplest one, right? But they exist in many steps of the life cycle, even in the data preparation step. So you don't just sit down, prepare the data, and at some point you're like, all right, good to go. You go through multiple steps of evaluating whether the data you have prepared is sufficient, is going to, ensure that you're covering all of the important use cases, can be derived consistently, and so on. So I think kind of the big push in the future for us is discovering what are the most important cycles or feedback loops that need to exist in the machine learning lifecycle, and how do we systematize and automate them as much as possible, minimizing kind of this human handover. And what are, I think, kind of the hardest part of this is what are some of the communication protocols? So how does, the production environment communicate with data annotation steps or feature processing steps in an automated fashion to essentially signal that something is not going right and something has to change?
Jan, do you have anything to add?
Yeah. I mean, it seems like we keep going back to the same thing, closing the loop, and then also for myself, the importance of diversity of raw data. So I'm just going to repeat myself again. I think, something that ML teams overlook, especially teams that are early in their ML development cycle, is the diversity of raw data. So early teams, they tend to focus on label accuracy because, they already have the raw data collected. They want to get the labels done and then just start training. But as teams mature, they will at some point hit a roadblock where their labels are 100% accurate, but their model accuracy isn't where it needs to be because it doesn't have enough data, right? So at that point, they need to focus on gathering more data, but not just any data, but expanding the coverage of their data set should be the key, right? So if teams wants to accelerate their ML development cycle, they need to start spending time and efforts into making sure that they have enough diversity of raw data before they run into this roadblock in the future, right? And then on a different point, so I also want to mention something that teams are actually overdoing instead of overlooking is when it comes to data quality control. I think too many teams are auditing or trying to audit the entire data set manually when they want to make sure the label quality, right? So like if you had an infinite amount of time and money to throw at that problem, sure, you can go ahead and audit your entire data set, right? But that's not the case for most teams. So for resource and time constrained teams, the goal should instead be fixing as many errors or mislabeled data as possible in the least amount of time, and then moving on to whether it's training the model or collecting more data, whatever, right? You don't want to stop there and spend too much time. And to do this, there are more intelligent ways to audit your annotations rather than random sampling. So like, for example, there are more intelligent ways to sample your data. And let's say your data set has 100,000 images and maybe 1,000 of them have errors, so mislabeled, so 1% error rate. If you can find and fix half of the errors, so like 500 images, by intelligently sampling and auditing like a small subset of the data set, like 10% of the data set, that's a huge win. So I think your time will be better spent collecting and labeling a fresh new set of data than trying to find the small number of errors. It's like finding a needle in a haystack. So yeah, something that I think teams are overdoing.
That's very nice. I agree. Thank you. It's the quantity of data can take you only so far, and then it starts to overfit. But the quality and like how good in your data is definitely the name of the game. I have questions. Good news, guys. So let's answer. A question from Justin. For an image-based object detection or classification model, how do you handle class overlap where multiple classes may have some commonalities in feature space? And any one of you guys?
I can take that. Thank you for the question, Justin. So I think you're talking about classes like pen versus pencil, or like, I don't know, truck versus bus, something that visually looks similar. I think if you have commonalities or multiple classes have commonalities in the feature space or embedding space, I think you want to optimize the embeddings so that the embedding representations can basically disentangle these multiple classes. That could be done using either algorithmically by using different or better performing embedding calculation deep learning models, or could be solved using data. More data, throw in more data that basically are near the decision boundary between these two classes, so that your embedding model can pick up the nuances of the different classes. And then this also applies when you want to change your class set. So let's say initially you start with a big, large set, like for example, for autonomous vehicles, let's say you start with a car class. Later down the line, you might want to split that into like taxi versus sedans versus whatever, right? And then you'll find out that within your data set, the embedding model that you trained on initially will cluster or will embed these car classes into the same or more or less similar embeddings. But once you change these classes into more granular class set, your embeddings model will then should learn to differentiate between these two multiple classes, right? Yeah. Anything you want to add? Yeah.
I think I should have read the both questions that he posted at the same time, because there is a follow-up kind of or explanation how to define an optimal category of annotation. How do you know when you need to create a new category of annotation?
Right. So, going back to my previous answer, there are multiple ways to do this, but, one way to do this is, do the embedding space calculations, see if your model picks up the differences. If it doesn't, one way to fix that is to, split into different classes. And there are, other ways to do it. This might be like overkill, but, this is one way to do it, I think.
Cool. Just wanted to make sure that I gave you the whole question.
Yeah.
Okay, we are 9:45. This is the end. Thank you, guys. Thank you, Alessia and Jan. Yeah, no, it's very abrupt. I really, I think it was incredible conversation. I learned a lot. Thank you everyone for joining. I hope you enjoyed listening to Alessia and Jan as much as I did. Yeah, thank you very much again, guys. That was awesome.
Thank you everyone for joining us.
Thank you. I really enjoyed the conversation and thanks for everybody who joined us.
Okay, thank you guys. Bye.
Bye.